Hello, welcome back to today's session. In today's session, we will be dealing with another problem called minimum cost spanning tree problem. So to solve this problem, we have two different algorithms. One is Kruskal's algorithm, other one is Prim's algorithm. In today's session, we will be learning the Kruskal's method or the Kruskal's algorithm of solving minimum cost spanning tree problem. Okay? So first of all, we need to know what is minimum cost spanning tree or minimal spanning tree. A minimum spanning tree is a subgraph of an undirected weighted network called G such that it satisfies certain number of conditions. The conditions are it should be a tree. What do you mean by a tree? What is the difference between a graph and a tree? You have learnt it in your second semester, data structures. Graph is a closed figure, a cyclic figure. But a tree is an open figure. Graph is a cyclic figure, tree is an acyclic figure. Okay? It is open in nature. It is not closed. Then it covers all the vertices V. That is, all the vertices specified in the problem. All the vertices specified in the problem should be present in the solution. No vertices can be eliminated. All the vertices should be present. But when it comes to the edges, all the edges need not be present. When I say subgraph, it means all the vertices or all the nodes of the network should be present, and these edges are arcs. You will have only V minus 1, that is the number of vertices minus 1. If you have 4 vertices, you will have 3 edges. If you have 5 vertices, you will have 4 edges. So V minus 1 number of edges should be present. See, only when you have V minus 1 edges, a graph remains a tree. If at all you increase even one more edge, if you make it V number of edges, then the tree will become a graph. Therefore, we are supposed to see to it that it covers all the vertices, all the V number of vertices, but it has V minus 1 number of edges. Clear? Next, the total cost associated with the tree. You would have created a tree, right? It would have weights. So these weights should be added up. That is called the total cost of the tree. The total cost associated with the tree is minimum along all possible spanning trees. See, if at all you consider a graph G, there is no compulsion that it should have only one spanning tree. It can have any number of spanning trees, but a minimum cost spanning tree can be unique. You understand? A minimum cost spanning tree can be unique, but a graph can have any number of spanning trees. So we will have a look at it in the example in the next slide. So as I said, there is the minimum cost spanning tree need not be unique all the time. It may be unique. If at all you have 2 or more edges which has the same weight, then there is always a possibility that instead of picking edge number 1, you can always pick edge number 2. So the solution may not be unique, but the total answer, the weight of the spanning tree is unique. The weight of the spanning tree is unique, but the minimum cost spanning tree that you get as a solution may not be unique. Clear? Hope you have understood the concept. So as I said, for constructing a minimum cost spanning tree, connect all the nodes at minimum cost. Our major aim or the objective or the goal of this problem is to see to it that all the vertices or all the nodes are connected, but it is connected with minimum cost edges. We connect them with minimum cost edges. That is the basic requirement or this is the basic goal of the problem. So if at all I consider, for an example, I have a network here with 3 vertices and 3 edges. So if at all I need to find the spanning tree for this, I can take any 2 edges. Any 2 edges I can take so that all the 3 vertices are connected. Right? So we will just have a look. So I can take edge number 1 and edge number 2. This will also form a spanning tree. I can take edge number 3 and edge number 2. This also forms a spanning tree. I can take edge number 1 and edge number 3. This also forms a spanning tree. All these are spanning trees. Right? All these are possible spanning trees of the graph. But I am interested in their weights. So what happens to the weight when I take this spanning tree? Its weight is 1 plus 2, 3. When I take the second spanning tree, 2 plus 3, 5 is the cost of the spanning tree. Here when I take the third spanning tree, cost becomes 1 plus 3, which is 4. So what am I interested in? What is the goal of the problem? The goal is to find the minimum cost spanning tree. Out of these 3 spanning trees, my minimum cost spanning tree will be this one. Right? The minimum cost spanning tree is 1 and 2. When it gets connected, it gives the total weight of the spanning tree as 3, and this is your minimal cost spanning tree. Hope you have understood the concept. So here, there is no compulsion that you need to start from a particular node. There is nothing called the source node and you are supposed to start the problem from the source node itself. There is no such compulsion. You can start from any node. Right? You can start from any node, and our basic goal is to attain or achieve the minimum cost spanning tree. Fine? So as I said, you may get a unique solution or you may not get a unique solution. When you don't get a unique solution, we will just have a look. Let me say I had these 3 edges of the same weight, 4, 4, 4. Then if at all I select the first edge and second edge, then also the weight of the spanning tree is 8. I take the second edge and the third edge, then also the weight of the spanning tree is 8. I take the first one and the third one, then also weight of the spanning tree is 8. The spanning tree is not unique. You can get any one of them as your solution, but the weight of the spanning tree is a unique solution. The weight of the spanning tree remains 8 only. It is unique. Okay? So if you pick any 2 of them, any 2 edges out of the 3 edges, you will get a spanning tree which is a minimum cost spanning tree. The value minimum cost spanning tree weight remains unique. Hope you have understood. Shall we move on? So as I said, to solve this problem, we have 2 methods or the 2 algorithms to solve this problem, minimum cost spanning tree problem. The algorithms are Kruskal's algorithm and Prim's algorithm. So in today's session, our focus is only on Kruskal's algorithm, which is one of the most simplest, easiest and fun-filled algorithm. As I said, it is very easy. It is more like a kid's play, right? So you will be able to solve this problem very easily using Kruskal's method. So we will have a look at the Kruskal's method now. What does the Kruskal's algorithm say? So first step in the algorithm is the initialization part. So what we are supposed to do in the initialization part? Create a set of each vertex V which belongs to V. So that is, you are supposed to create a set of all vertices. See how many vertices are present in this diagram? A, B, C, D and E. You have 5 vertices. So in your solution also, you need to have, you should have, you must have, you ought to have 5 vertices. So there is no compromise in the number of vertices. The number of vertices present in the problem should be present in the solution as well. So that is why I am creating a list of all the vertices that are present. So I am creating a set of each vertex V which belongs to the vertex set V. Okay? So we are creating this separate sets. A is a separate set, B is a separate set, C is a separate set, D is a separate set and E is a separate set. Each vertex is formed as a separate set, and this set of all sets, we call it as a forest. Why do we call it a forest? A group of trees is called a forest. So here each vertex is a tree in itself, right? Each individual isolated vertex is a tree in itself. So therefore, A is a separate tree, B is a separate tree, C is a separate tree, D is a separate tree, E is a separate tree. So 5 separate trees we have, and we are putting it as one set. Therefore, I call this set as forest. That is why I am representing it as F. Okay? Next, second step of initialization. Initialize a set of safe edges A comprising the minimum spanning tree to the empty set. Initially, the solution that we are supposed to form does not have any edges, right? Our final solution will be in form of a set of edges, right? But initially, I don't have any edge in it. Therefore, I am initializing A as a null set. So I will create A as a null set. Hope you have understood. So the third step of initialization says, create an edge list called E. How do you create an edge list? In a sorted order, right? In the edge set E, sort edges by increasing order of their weights. In the ascending order of the weights, arrange all the edges. See here, out of all the weights, which is the minimum weight? 2. So AD comes first. Then after that, CD with 4, DE with 4, then AC with 5, then BE with 5, CE with 5, BD with 6, AB with 9, right? In the ascending order, I have created a set of all edges. So hope all these 3 steps are understood. First step, create a forest. Second step, create a null set. Third step, create all edges, you call it the edge list E, right? After you have done this, the next job is pick every edge one after the other from the edge list. For each edge u comma v belongs to E in increasing order while more than one set remains. See, in the forest, you should have more than one set. Till then, what you will do, you will pick one edge from edge list E and check whether U belongs to a separate set and V belongs to a separate set. If U and V belong to different sets U and V, then that is a feasible safe edge. We call it as a safe edge. So because it is a safe edge, you add it onto your solution set A. So A is equal to A union U comma V. So I'll add this edge onto my solution tree. Then merge the sets U and V. Fine. These two sets have to be merged into one set in the forest. Let me say I considered the edge 1 to 2. 1 was in a separate set, 2 was in a separate set. So it was a safe edge. I added them into my tree. Now they are joined. They are part of the same tree. Therefore, in the forest, I am supposed to merge these two edges. These two sets have to be merged. So I will make the set as 1 comma 2. Okay. This process is repeated till in the forest I am left out with a single set. Right? In the forest, I should remain with a single set. This process is your Kruskal's algorithm. Is it tough? No, right? So we will try to solve a problem using Kruskal's algorithm. So the first problem, so the number of vertices that I have is 5, A, B, C, D, E. So first I will create a forest A, B, C, D, E. Then I will create a solution set A, which is initialized to null set. Then I am creating an edge set AD with 2, CD with 4, DE with 4, AC with 5, BE with 5, CE with 5, BD with 6 and AB with 9. Okay. Now my actual algorithm process begins. So first I will pick the first set, first edge AD. So I will check in the forest. A is a separate set, D is a separate set. So it is a safe edge. Add it onto A. So in A, I'll add this edge A comma D. And in the forest, I will merge A and D. So AD becomes a single set. AD and remaining B, C, E are separate sets. Okay. And once I have used this edge, I just cross it out because I don't want to consider the same edge repeatedly. So this I have removed. Next edge that I had was CD. So take CD. C is in a separate set. D is in a separate set. So it is a safe edge. So add it onto the solution set. So now your solution tree has AD and CD. Okay. Now merge the sets in the forest. So you get A, D, C as one set, B is a separate set, E is a separate set. Fine. Next edge in the list is DE. Check D and E. D is in one set, E is in another set. Because they are in different sets, it is a safe edge. Add it onto the solution tree. So your solution tree has AD, CD, DE. Now in the forest, these two sets are merged. So you get ADCE as one tree and B as a separate set. Okay. Now in the set, look at AC, A and C. Both are in the same set. So it is not a safe edge. So I am not adding it onto the tree, nor am I merging any set. I am just moving on to the next edge in the list. The next edge in the list is BE. So B is in a separate set, E is in a separate set. So they both are in different sets. So add BE into the solution set. So your solution tree becomes AD, CD, DE, BE. And your forest becomes ADCEB. I am remaining with a single set. Once I reach a single set, my solution or my problem is solved. I need not check the remaining edges in the edge list. I have already arrived at my minimum spanning tree, right? So let us construct a spanning tree out of the solution tree that I have got. Whatever set I have got in A, using that I am supposed to construct a minimum spanning tree. So first write all the vertices A, B, C, D and E in its original places. First join AD and its weight is 2. Then join CD, its weight is 4. Then join DE, its weight is 4. Then join BE, its weight is 5. So after joining all this, what is our next job? Find the total weight of the spanning tree. So the weight of the spanning tree is 2 plus 4 plus 4 plus 5. So this is your first standard addition. Add it up. 4 plus 4 8 plus 2 10, 10 plus 5 15. So weight of the spanning tree is 15 units. Isn't it simple? Isn't it easy? Okay. Let us try to solve one more problem using Kruskal's algorithm. Problem number 2. So first, create a forest. So 1, 2, 3, 4, 5, 6. 6 vertices I have. So I create a forest. 1, 2, 3, 4, 5, 6. And I create solution set A, which is null set. Then create an edge list in the increasing order of weights. 1 to 2 with 1, 3 6 with 2, 4 5, 4 5 with 6, then 1 3, 1 3 with 9, then 5 6, 5 6 with 9, then 2 3, 2 3 with 10, 3 4, 3 to 4 with 11, 1 6, 1 to 6 with 14, 2 4, 2 to 4 with 15. So in the increasing order, I have created the edge list. My initialization process is done. Now we go to the solution part of or the solution process of Kruskal's algorithm. So first, pick the first edge 1 to 2. 1 is a separate set, 2 is a separate set. So add it onto the solution tree. 1, 2 gets added. 1 and 2 are merged. So 1, 2 is a separate set. 3, 4, 5, 6 are separate sets. Then pick the second edge 3, 6. So 3, 6 both are in different sets. So add it onto the edge list. So 1, 2 is one edge. 3, 6 is another edge in the solution tree. Now merge the set 3 and 6. So I get 1, 2 as one set, 3, 6 as another set, 4 and 5 as separate sets individually. Then pick the next edge in the edge list, 4, 5. So 4 is a separate set, 5 is a separate set. Because they are different sets, it is a safe edge. Add it onto the edge tree or your solution tree. So your solution tree now has 1, 2, 3, 6 and 4, 5. Okay. So now merge the sets. So you get 1, 2 as one set, 3, 6 another other set, 4, 5 as another set. So how many sets are there? 3 sets. So still you have not arrived at the solution. Go pick the next set. The next edge is 1, 3. So 1 is in set number 1, 3 is in set number 2. So they are in 2 separate sets. So it is a safe edge. Add it on to the solution tree. So your solution tree now has 1, 2, 3, 6, 4, 5, 1, 3. Then perform the merge. So you now get 1, 2, 3, 6. These two sets are merged together. So you get 1, 2, 3, 6 as one set, 4, 5 as another set. So you have two sets now. So still you have not arrived at the solution. So what are you supposed to do? Pick another edge. The next edge is 5, 6. So 5 is in set number 2, 6 is in set number 1. So because they both are in separate sets, it is a safe edge. Add it onto the solution tree. So your solution tree becomes 1, 2, 3, 6, 4, 5, 1, 3, 5, 6. Perform a merge in the forest. So you get 1, 2, 3, 4, 5, 6, a single set. So because you have arrived at a single set in the forest, you have finally arrived at the solution. And this is your solution tree. 1, 2, 3, 6, 4, 5, 1, 3, 5, 6. Using this, construct a minimum cost spanning tree. So first 1 to 2. Join 1 to 2. Its weight is 1. Then join 3 to 6. 3 to 6. Its weight is 2. Then join 4 and 5. 4 and 5 with weight 6. Then join 1 and 3 with weight 9. Then join 5 and 6 with weight 9. So what will be the weight of the spanning tree? 1 plus 2 plus 6 plus 9 plus 9. 9, 9, 18, 18, 6, 24, 24, 2, 26, 26, 1, 27. So weight of the spanning tree total is 27 units. Isn't it simple? That's it. So this is your Kruskal's algorithm. Hope you people have understood and enjoyed it. Thank you for your patient listening. In the next session, we will be dealing with Prim's algorithm. Till then, have a nice time and enjoy. Thank you for your patient listening. Thank you. Bye.